Welcome, everybody. Thanks for joining me around the telescope. Saw this article, actually two articles that came out, and the article that I'm making, The Anatomy of an Explosion, How Massive Stars Prepare for Their Final Act, very interesting. Two key papers came out on this. The first is Critical Metallicity of Cool Supergiant Formation, 2, Physical Origin, and there's a link if you go over to EZ Astronomy right there that you can get it. And the second is Multiwavelength Signatures of Supernova Shock Breakout from Red Supergiants in 2 dimensions, and the link's there for the paper. The papers are well worth going through the time to read them. I'm just basically hitting on the highlights. There's a lot more in depth on the paper, so I highly recommend that you go there and take a look at it. Every once in a while, astronomers run into a stellar explosion that refuses to follow the rules. It just doesn't go by what they think it should go by. Most supernovae follow a fairly predictable script. A star reaches the end of its life, it collapses or detonates, brightens rapidly, and then fades away as the radioactive elements decay. But modern sky surveys are discovering more and more events that simply don't behave the way that textbooks say they should. And we've posted about some of those findings, and we'll continue to share those as they come up. 2 recent research papers published in the Astrophysical Journal explore this strange territory. They investigate unusual stellar explosions that change type, brighten again after fading, or interact with their surroundings in unexpected ways. Excuse me on that. For amateur astronomers who follow the supernova discoveries or who spend time hunting faint remnants in large telescopes or imaging them, these papers reveal something very important. The death of a star is often far messier than we once believed. Let's take a closer look at what these studies found and why they matter. Paper 1, a supernova that changed its mind. The first paper focuses on a rare object, a type-changing stripped envelope supernova. To unpack that phrase, we need to get a quick refresher. The usual stripped envelope supernova story. Massive stars often lose their outer layers before they explode. When this happens, astronomers classify the resulting supernova based on which elements appear in its spectrum. We did a video on this. So as a reminder, the main stripped envelope types are a type 2b, retains little hydrogen, a type 1b, hydrogen is mostly gone, and type 1c, hydrogen and helium are both gone. These categories reflect how much of a star's outer layers were lost before the supernova explosion happened. Normally, once the explosion happens, the spectral type doesn't change. But in this case, it did. That's what was weird. The light curve was really weird. The star first exploded and behaved like a typical stripped envelope supernova. But then something strange happened. After beginning to fade, the object brightened dramatically again. This kind of rebrightening is extremely rare. The light curve, essentially the brightness versus the time graph, develop multiple peaks instead of one. Usually a supernova, and I've shared that, they have a peak and then they either stay or they decline rapidly, they even out over time. This one, multiple peaks in that light curve. After beginning to fade, the object brightened dramatically again. This kind of rebrightening is extremely rare. The light curve, essentially the brightness versus the time graph, like I said, developed multiple peaks instead of one. To astronomers, this meant that something energetic occurred after that initial explosion. What caused the second brightening? The most likely explanation is interaction with circumstellar material. In simpler terms, before exploding, the star expelled large amounts of gas into space. When the expanding supernova debris slammed into that material, the collision converted kinetic energy into light, causing the star to brighten again. Think of it like a cosmic traffic accident. The supernova blast wave expands outward. It hits shells of glass previously shed by the star. The collision heats that gas to millions of degrees, and this system grows brighter again. So why did the star shed so much material? That's the real mystery. The observation suggests the star underwent violent mass loss shortly before exploding, possibly years or decades beforehand. Several mechanisms could have caused this. Could have been an unstable nuclear burning inside the core, interactions with a close binary companion. Just did a post on that last week. eruptive mass loss similar to luminous blue variables. In other words, the star may have experienced a chaotic final phase before its death. Why does it matter? For decades, astronomers assumed stripped envelopes in supernova were relatively clean explosions. But events like this show something else entirely. The star's final years may involve violent outbursts and shell ejections. The stars, when the supernova shockwave later plows into those shells, we see strange light curves and spectral changes. So that was the first paper. I'm going to end it there because I want to be able to, we're going to do each video on each paper and then an ending segment. So come back to me in just a second, watch this video 2 on this and the second paper. Just fascinating stuff going on here. Love the life cycle of stars. One of my favorite books is The Birth and Life and Death of Stars by Kenneth Lang. Awesome book. Anyway, catch you in a few minutes. Thanks for joining me.